Hi again. My name is Michael Hansen, as I've said in some other videos. Let's just do the full introduction. I'm a master student at the University of Copenhagen. I'm currently writing my master thesis about in astrophysics about gravitational lensing in galaxy clusters. In reality, it's more about the dark matter than matter distribution in galaxy clusters that I can model and then infer from gravitational lensing, gravitational lensed images. Yeah. So it feels almost like we're beginning to know each other here, or at least you're beginning to know me. I know nothing about you, but that's the way it works, I guess. Alright, another question has popped up. And I would like to stress again very firmly, I have done that in 2 answers to the person raising this question. Science is not about proving things. Science can never prove a thing. Not a thing. Because again, in order to prove something, you have to say, now it is within no doubt sure that I have the correct answer. And then you have to ask yourself, how many experiments, how many measurements do I have to take in order to, with 100% certainty, say that now I have the correct answer? You can't. You would have to do an infinite number of experiments in order to make sure that you had the correct answer. What science does is it tries to disprove or refute claims. So if I say something like, let's say that gravity is in reality an electrical force, then in order to back that claim up, I have to do an experiment. Now, I could doctor that experiment, or I can rewrite my results in order to show what I wanted. But in order for my claim to be accepted in the scientific community, I have to release my method and at best also my results, not my calculated results but my data stream, in order for other people to reproduce my experiment and to see if they get the same result as I do. Now, if many people in the scientific community don't get the result I get, which they probably will, considering what I proposed, then my claim will be considered refuted or disproven. But if many people in the scientific community do the same experiment that I did and get the same results as I did, then my experiment is, or my claim is considered not yet refuted. And if I make a collection of ideas, sort of a broader aspect of explanations for certain things in science, and they get tested and can't be refuted, then my claims will probably get the status as a scientific theory. So again, science does not prove. If you want proof, then you have to go somewhere else, to philosophers or church or mosque or synagogue, depending on your religion. But in science we don't deal with truth or proof because we can't prove it. Sort of math can prove things, but that's a different league. That's also a very different method. Alright, so there is a science that can do science that can do proving, and that is math. But physics, chemistry, so on, biology cannot do proving. We can't prove things with absolute certainty, and we never will. Alright, so the question is, how do I know the distance to Polaris? How can I prove it? I can't prove it, but I can show you how I can find the distance to Polaris. Alright, so let's delve into something that we hopefully all can agree on, we know, and hopefully also is considered true, that is high school math. Alright, I hope you all know the tangent rule in trigonometry, but basically, if I'm standing here that's me. And I can see some tower over here. I know the height of the tower. Let's call that, I'll do A. I would like to know the distance. I call that B. And I also know the, let's put a little antenna here. I also know the angle. Let's call that big A. So the tangent rule says that the tangent of A is equal to the opposite divided by the concurrent, or what it's called. And then if I want to find B, then I can just rearrange this to get that B is equal to A over tan A. Now this is easy to test, this is easy to prove. You can just just place a dot on a piece of paper and a line, then you can measure the height of the line and measure the angle, and then you can calculate how long the distance on the paper is without knowing it, and then afterwards you can measure it to see if you are correct. If you want to do it in a more elaborate way, you can go out into the actual real world, place a stick in the ground, measure the height of the stick, go a distance away you don't know, and then find some way to measure the angle up to the top of the stick from the ground. And then you can calculate the distance and then later measure it. Within some reasonable uncertainty you should get the correct distance. But that may depend on the height of the ground or balls, what do you call it, small hills or whatever that may be in the ground that can skew the angle. Alright. In astronomy we have sort of the same basic idea. So what we do is that if I have a point here, I have an angle here that I call alpha, I have a distance here called small r, and a distance here I call big R. Now, in astronomy we use what we call the small angular approximation. That is also mathematically proven. That sinus to alpha is equal to, or almost equal to, alpha. The same with the tangent, that's the same. That might be more reasonable. And this tangent to alpha is approximately equal to alpha. Alright, so what I say here is basically the same idea, that my big R is equal to small r over my alpha. Now, in astronomy we have designed or derived a distance called a parsec, which really is per arsec, that's why it's called what it's called. And it's really easy to define. If I have that alpha is equal to 1 arcsecond, I have little r is equal to 1 astronomical unit. You can later consider why that is chosen. Then I have that r, big R, is equal to 1 parsec. Alright, with that in mind, let's just erase most of what I put in here, and then say that big R is equal to 1 AU over alpha. Big R would be the distance to the star I want to know, alpha would be the parallax angle of that star. Now, the reason why that AU is chosen is that the distance from the Sun to the Earth is 1 AU. Alright? So let's say at two opposite dates I measure the angle to Polaris, that is up here, from here, and then I do it from here. This is the parallax angle alpha. Then by again the same basic trigonometry, by finding the distance up here, I know what the angle is compared to background stars. And since I know that the distance from Earth to the Sun is 1 AU, I just plot in the numbers. Now I found that the alpha for Polaris is approximately, we see, 7.5 times 10 to the minus 3 arcsecond. So let's put that in. R is equal to 1 over 7.5 times 10 to the minus 3. And that is approximately equal to, let's just do like this, because I'm not entirely sure of the numbers, 133 parsec. Now I know that 1 parsec is approximately equal to 4 light years. So the distance to Polaris from us is approximately somewhere around, let's just say 500 light years, 400 something, but approximately 500 light years. Alright, so that is how you calculate the parallax distance to Polaris. That is actually quite simple. It's simple trigonometry. Alright, I'm not sure how much time I have left, so I will cut the video now and then I will continue in the next video by talking some more about how do we actually measure the angle, what is doable from Earth, and so on.